Hello, in this particular demo we're going to have a look at steering behaviors within sort of a simple example Android program. There'll be a two-part demo. In the first part we'll have a look at the actual demo we're developing here. It builds upon the architecture that was previously introduced, so we want to have a look at how it does that, what type of classes does it introduce, and how do those classes link in with the managers and the other things that are available within our architecture. Second part of the demo then, we'll look at specifically the objects we're creating here and how they make use of the different steering behaviors, and we'll have a look at those. So we'll start off first of all just by running our demo, so we get a bit of a feel as to what we will be looking at. When the demo runs, you get a simple, and this is a remarkably simple menu screen. It's probably insulting to menu screens to call this a menu screen, but nonetheless this is what we're going to call it. On this we have two buttons, really just images, and if I click on either of those buttons, then it's going to take me off to the particular demo that I'm going to be having a look at. So there is a sort of a collision based one we're not looking at in this one, and we also have our steering behavior. So when I click here, it takes me off to my steering example. For the steering example, I've got a player controlled spaceship, and if I click, it will move around the screen. Depending on where I click, that will determine the direction relative to the center of the acceleration. I also have a bunch of objects, and these you've got asteroids, you've got a turret, and sort of seeker ships, and they're created at random whenever you introduce or start up with the level, so it's just random as to where they appear. In terms of the steering behaviors that they're using, the turrets that we have here, they will always try to look towards the player. So as the player moves around, they change their orientation so that they are pointing towards the player. And the other ships that we have, the ones that are trying to seek the player, their behavior is set up that they will head towards the player, but they will also try not to collide with the player, not to collide with themselves, and not to collide with the asteroids or the turrets. And they based on the accelerations they have, you can see that, well, they try to do this, but sometimes they actually do overlap with it. But we're using a number of different forms of steering behavior within this. The player ship, it is looking in the direction it is moving in. The turrets, they are constantly trying to look at the player. And the green seekers that we have here, they're trying to seek towards the player, look in the direction they're traveling, and to separate from a number of different collections of objects. So their behaviors combine several different elements. So let's have a look at how we can bring that about. And we'll start off for this particular half of the overall talk, looking at the classes that we've put in, and then how do they tie in with the engine. So what we're going to have here is our main demo game, which is going to build upon our game class. This is our fragment. We're going to have a game screen. So inside our world, we said our world comprises a number of screens, and those screens contain a number of game objects. So our menu screen is going to be a type of game screen. And inside my platform demo, I also have inside my space demo, which is the one for steering, I have a steering demo game screen. So that I've got two screens within my particular simple game here. Menu one, and then a second one containing the ships that we're doing all the steering, and the players one. For game objects, I really have only three types of game objects in this. I've got the player, I've got the asteroid, and I've got the AI controlled spaceship. We could have had, for example, a specific object for a button and put this into the menu screen. That would be a reasonable extension for it, but for this particular demo that wasn't done, or we don't have it. So let's have a look at our demo game first of all. So it extends game, and game is our fragment that contained a single full screen view that also contained all of the different managers and things that helped us bring a game to life. So when we create it, we have to make sure we call the Superclass. It's obviously a sensible thing to do to make sure that we're doing what the game's base class is doing. At this level here, we're overriding methods within the underlying class. So we've got the onCreate and onCreateView, and then we've got one final OnBikePress method here. Now, if I go into my game, and I find, for example, the onCreate method, you'll see that when I'm creating the game, there's various things I can do when I simply build the object in terms of getting the loop, file systems, asset manager, screens managers. And when I create the view, there's a few more things I add in terms of my input manager linked to the view, a renderer for the view, and get some metrics. So inside my demo game here, I'm overloading the onCreate and onCreateView. It's essential that I make sure that I call the Superclass version, that I don't simply replace and totally the functionality, but I'm adding to that functionality. So I have to remember that I call the Superclass. On the onCreate, the only thing I'm doing here is setting up to, well, 20, 30, let's go back to 20 as what the comment says. I'm setting up the default number of updates per second. OnCreateView, and for most games, this is where you want to put your content into this particular point. The reason for that is that it's only whenever we are creating the view that we actually have something we can potentially draw to, that we will know how big the screen that we have is. So if we're going to do any setups in terms of sizing screen viewports or things like that, then that's activities we have to put within the onCreateView. OnCreateView is a method that returns a view. How do I get the view that I return? I'm going to my Superclass and I'm calling the Superclass's onCreateView and passing in these values, and it gives me back the view. So I'm getting that from the Superclass constructor, and that's what I'm returning at the end. So I'm not breaking, if you like, the assumptions as to how this works. What we're inserting, if you like, into the middle that is specific to this particular game is we're saying, okay, let's create a new menu screen that belongs to this game. And let's go to my screen manager. Screen manager is what I inherit from the underlying game, so I just have it directly. And I add in, this particular menu screen that I'm just after creating. The screen manager is set up so that it assumes that it doesn't have any screens, and you add one in, it automatically becomes the current screen. So effectively, here I am saying to the game, this is the initial screen that I would like to use and to have updated and have displayed. I've got a bit put in here for the back key when it's pressed, and if we just go up a little bit. So here we have our main activity. This is in the architecture, and we've overloaded the OnBikePress. So all activities will have an OnBikePress method that gets to be called whenever the back key is pressed. And if I don't do anything, if I just simply call the super OnBikePress, then we get the default behavior that happens. That activity, if you like, will be removed, and whatever was before it will kick into place, or will exit out of the application if there was nothing before it. I'm overloading this now, so what I'm saying here is that when there's a back pressed, go to the game fragment and let it know that there has been a back button has been pressed. And if it returns back true, what that means then is what I'm assuming, or what I'm interpreting it to mean here, is that it has consumed the back press. So effectively it has dealt with it in an appropriate way, and I don't need to do anything else in addition to it. If it returns false, so if the fragment or the game says it gives us back a value of false, what that means is that it hasn't handled or has not had anything specific to do in terms of the back press, and I should then invoke the default behavior for the back press. So within the game, this won't do very much for this particular version here. So the default game fragment, OnBikePress automatically returns false. So by default it says, I'm not going to do anything with it, just use the default one. But if we have a look then at our demo game that we've created here, You can see actually we are overloading the OnBikePress because we want to have a bit of control. In particular, the control we want to have is that if I was playing the steering game and I hit the back key, I should go back to the main menu. And if I hit the back key from the main menu, then I should exit out of the game. So we are changing the behavior of the back key here to see, right, let me check the current screen that we're on. If it is the main menu, then I can't go up any more screens. So I return false, which means I get the default behavior being executed. If that isn't the case, then what I'm doing here is that I am removing a screen from the screen manager, and I'm creating a new menu screen and then adding that into the screen manager and returning true, signifying that, oh, I have actually processed it. So you don't need to do anything beyond that. So just a way of us being able to control what happens. That's our main fragment of the demo game in terms of how we overload that. If we have a look at the menu screen as our next class, so this is a type of game screen, and it embeds that excuse of a menu where we had a couple of different images displayed on the screen, which we could click on one of the images. I mean, it's crudely a menu of sorts. We'll have a look at how this works. Just in terms of giving you an overview of the class, we've got a couple of rectangles, one for our spaceship demo, one for our platform demo. These rectangles define the region that we draw the icons to, and also define the regions within which we check for touch events. So effectively, they trigger where things are well, touch events will act as a trigger, and they also control what's displayed. When we create our new menu screen, we're making sure to call the Superclass, and we're saying that the name of this particular screen is menu screen, so that we can query or get that out within the game. We are going to our game, so all screens have access to the game within which they belong. And we're asking the game to say, okay, you contain the asset manager, can you lend me it, please? So we're getting the asset manager. And we're using the asset manager to load in a couple of our spaceship icons and our platform icons. The things that we'll be displaying, if you like, notionally as our buttons. Having done that, we also go to the game and get the width and height of the screen. We use that to provide a bound, a region of the screen that we're drawing our spaceship and platform. In this case, we're chopping into 6 1/3, and so we will have sort of a square-like region then for each of those different buttons. One thing that's worthwhile saying here is the asset manager. The whole reason we have an asset manager is to share assets amongst game objects so that we can load in one particular graphic or one particular sound, and the asset manager, it holds on to it, it looks after it, and if a game object needs to get access to it, then it doesn't load in its own copy, it goes to the asset manager and it gets a reference to the one single version. So it was a good way of efficiently managing the assets that we have. Now in this particular case, the asset manager here, arguably you could say you don't need it, because the spaceship icons and the platform icons, they are only ever used within this menu class. So we're not reusing them or sharing them or putting them somewhere else. So arguably it's a little bit of overkill to get the asset manager to load them in, to hold on to it, where the only person or the only entity using them is this particular menu screen. So you could have just loaded them in directly here and had the menu screen hold them. But by way of illustrating how the asset manager is used, by way of sort of adhering to the principle that it is the asset manager that looks after all of these things, this is what we're using in this case. Underneath that we have our update and we have our draw method. So the update method, we'll have a look at that one first of all. We want to get and to query touch events, so we need our input manager. The input manager is something that is managed by or held within the game. So we go to our game and say, okay, give me access to the input manager, please. And we're then checking to see, okay, for this most recent update. So remember, we're calling this menus update, in this case, say 20 times a second. So we'll have a 20th of a second roughly between each of the invocations of the method. And during that 20th of a second, we might have had some touch events occur within it. And the input manager will package up all of the touch events that occurred since the last time our update was called, and provided us with them in terms of a list. Now that list could be empty if we're not touching anything. It could contain multiple events if we're dragging our fingers across the screen. It could contain a single event. But we're checking to see here, do we have a touch event? Now, if we do, all I'm doing at this point is getting the first touch event that has occurred. I'm ignoring the possibility that there may have been several touch events. And this is a limitation in as far as what this means then, there are certain ways I could potentially interact with my screen by putting down multiple fingers and moving them about simultaneously, which would mean that I would notionally miss a triggering event here, because I'm only looking at the first one. It's acceptable in this case because it's a simple demo. It's also acceptable in this case because I'm presenting a few buttons. Generally speaking, in that case, the user will be inclined to simply touch one button at a time. They're not going to be putting several fingers down onto the screen. And if they do, and it doesn't behave as they're expecting it, well, that's their problem. So anyway, we get the first touch event, and we then go and we have a look. So this is a rec, the Android rec class. It has a method contains, where I can pass in a point, and it's going to tell me whether or not the particular point is contained within that rectangle. So I'm passing in the X and the Y location, which will be screen coordinates, so my rectangle has to be expressed in terms of screen coordinates. And if I do touch that particular rectangle, this if will trigger. And what I do there is that I am removing the menu screen, and I am adding in a new steering demo screen. I'm actually creating the screen, then I'm adding the thing in. Little bit of a side there, because there are different ways you could be using the screen manager. This is one way. For a complex game, arguably you wouldn't want to use it in this way. For this one, I'm removing screens and then creating and adding screens in. I could also have used the approach of creating the game screen, the manager at the start, creating a menu screen, a level screen, and adding them all in, so the screen manager holds instances of all of these screens. And if I want to change, then all I change is the current screen. So I don't add or remove screens to it, I just swap the one that is current. But in this case, I'm actually removing the menu and then creating a new one and adding it in. So it's just one way of doing it, but not necessarily a right or a wrong way. The else if is for the platform. We'll check to see if it's being pressed. If so, do a similar pattern. Remove the menu, create a new demo screen, add the thing in. Finally, at the bottom, we have our draw behavior, where we're drawing it out. There we're going to our asset manager, we're getting out the bitmap. We could have stored it at the top if we wanted to. Clearing the screen to white and drawing out the bitmap within the region, the touch region that we have defined. So it very clearly then delimitates the areas that we're anticipating that the player will interact with. So that's our very simple menu screen. For the space demo, there's a few classes within this one here. Now, in the second part of the demo, we'll have a look at the player spaceship and the AI spaceship in a bit more detail. Here we'll just look at the Asteroid as an example game object, and the game screen in terms of how they are put together. So if we have a look at the Asteroid, Asteroid extends Sprite, so we'll have a look at Sprite in a second. It's making use of a static random, because anytime you create an asteroid, we want to randomly position things. So as opposed to creating a random object and then discarding it within the constructor, I'm creating a static one that is an object that all instances of asteroid can reuse. It's a little bit more efficient. All I'm doing in the asteroid is, as you can see, it's constructor. The rest of the things about how we update it, how we draw it, these are simply done through the sprites update and sprites draw, which we'll look at in a little bit. So when I create an asteroid, I say where I want it to be created, located, and I say the screen to which that game object belongs. And I'm calling the Superclass constructor to pass in the starting location. Here I'm giving it a fixed width and a fixed height. I'm not giving it any image at this point, but I am saying there's the screen you belong to. So The Superclass constructor, it will do part of the construction. It will give it its position, it will give it its size, it will not set up any bitmap for it, but it will remember the screen to which it belongs. What I do in the rest of this then is I define the rest of the values. So I want to give it a bitmap. So I'm going to, this is a game object, it belongs to a screen, so I go to the screen. The screen has access to the game in which it belongs, I go to there. And the game has access to the asset manager, so that's eventually what I want to get. And from the asset manager, I want to get out a bitmap. Now, whenever I'm sort of loading up this particular demo, and we'll look at that in a second, look at the screen, I'll load in a number of images. And I will load in 2 images for the asteroid. So there's 2 different ways the asteroids can look. So I just randomly pick one or the other. So it gives a bit of visual variety in terms of the appearance of the asteroids. I'm setting up the half width and half bound. Okay, it's really sort of specified there as well. And I'm also defining an angular velocity for it. So I want all of these asteroids to rotate. And they are rotating with a value between -20 at the lowest up till +20 degrees per second at the maximum. So simple setup. Have a look at the Sprite class, because Asteroid's a type of sprite, as is AI spaceship, as is the player spaceship. So all of these are building upon our sprite. Sprite's also a type of game object. Let's go up and look at game object first of all. So a game object, so these are the things that live within our game screen. A game object belongs to a screen, fair enough. It has a bitmap, probably fair enough assumption. Some of them may want to use things more sophisticated in the bitmap, but there you go. It has a position, and I'm using my sort of vector class, which again I'll have a look at in a second, just by unraveling this sequence. It has a bounding box as to its location, its width and its height. And we've got a couple of reusable rectangles we're using when we're drawing it. There's a number of different types of constructors here where you can give it, locations, a bitmap, or you can specify particular widths and heights or things like that. I've got some methods. I can get out its bound, I can get out its bitmap, I can set its position, update. I have an update method, so all game objects can be updated, but at this particular level, update does nothing. So it's up to the refining classes to say what update actually means. I do have a default draw behavior that all of them will inherit, but again, you can overload if you want to. This will simply draw it, given a time information, a graphics object used to draw it, and some viewport information. It basically checks to see if it is visible, what are the rectangles, then draws the thing out. So that's our game object. What sits above game objects then are sprites, so they are a type of game object. And a sprite, I've assumed here a sprite is something that steering behaviors can operate on. So it's a fundamental thing to having steering behaviors. If we want to have steering behaviors, we need a position. We get that in the game object. We need to have a velocity. We're going to have to add it in here. We need to have an acceleration. Ditto, we need to have it add it in here. These can be linear accelerations, or it can also be angular accelerations and angular velocities. So I've got a bunch of maximum or default maximum values at the top. If we want to say just how fast any of these can move, in the minute they're unbounded, but you could bound them depending on your game. We have a velocity and an acceleration vector. Look at this class in a second. We have a maximum acceleration and maximum velocity. This is the magnitude of the acceleration and magnitude of the velocity in terms of the speed. And we're setting those to the default, but again, they can be changed by the calling class, and we will change them when we look at the player and the AI controlled ship. Orientation, which is the angle at which this object is facing. Angular velocity is the rate at which the orientation is changing, and angular acceleration is the rate at which the angular velocity is changing. So we'll use those within the steering algorithms, and again we've got maximum values defined for how quickly it can turn. If we're drawing these things out rotated, we're going to have to use a matrix within the draw components. We'll be calling draw frequently. We don't want to keep creating matrices. So we make use here of a sort of a created up front and then reuse it within the object. For creating a sprite, again, we've got a bunch of constructors, mostly map onto the ones in the game object. If we're updating a sprite, so here we actually do something. In the game object's update, it was empty. In this case, we do have some meaningful update to do. And if you think back to the Asteroid class, I'd like to have it here, it doesn't have an update, doesn't have a draw, so it is making use of the inherited one that we get in this case. What we're doing is we're taking out how much time has elapsed since it was last called. We're making sure that the acceleration that I'm using at the minute isn't too strong. So potentially some of the steering behaviors could have given an acceleration, and maybe that acceleration was too big, but we'll just do a check here to make sure that it isn't too strong. We're using length squared. I'll talk about that when I look at the vector class. And if it is too strong, then we normalize the acceleration, bring it down to length 1, and then scale it back up to the maximum acceleration we have. So we retain the direction, but change the size. Given acceleration, we can use this to update our velocity based on how much time has elapsed. Now that we've updated the velocity, we check to make sure our velocity hasn't exceeded the maximum, and if it has, then we restrain that speed. Given a valid velocity, we then go and we update our position, again taking into account the period of time that has elapsed. And that's changed or potentially changed the position of the object. We're doing more or less exactly the same things for the angular acceleration. We check to see that our angular acceleration isn't too strong. If it is, then we restrict it. Signum, the Mas signum function, if it's a positive value, it returns 1. If it's a negative value, it returns -1. So it's an easy way of sort of working out this should be a positive or negative maximum acceleration. Given the angular velocity, we update that using the angular acceleration. We check here that our angular acceleration isn't too fast, scaling it back if we need to. And finally, we update the orientation. For drawing it out, now, the game object did have a default draw behavior, but we need to overload, we need to change it in this case because we're using our matrix, because maybe we're going to be rotating these things. So we see if it's visible, we see the regions, things like that. If need be, we sort of scale, and then we're setting up our matrix here, where we're setting it, we're scaling it as need be. We are then rotating it out around the center, the scaled center of the bitmap, so rotating about the center, and we're then drawing it or translating it to the right location on the screen, and then finally drawing it out. Okay, so that's the Sprite class. I want to show you the Vector2 class as well. We're talking a lot about velocities, accelerations, positions. In a two-dimensional game, they have an X, they have a Y coordinate. And we don't want to keep passing in two separate X and Y values. So we want a class that basically packages together an X and a Y. So we're creating our own class here called Vector2. So it's a two-dimensional vector, I suppose they're a three-dimensional vector. We're using floating point values, so we've given one X component, one Y component. And the rest of the things we have within this then are basically a bunch of constructors for building them, a few methods checking to see is it of zero length, or what is the length, or the length squared. Now, some of the tests, for example, if we're testing if the length of a vector exceeds a particular distance, I could either say I've got my target distance, I'm going to call length, and I'll check to see if length is greater than this target distance. Or I could say I'm going to call length squared and check to see if the length squared is greater than the square of the target distance. So I could take my target distance, square it, and compare it against the length squared. That may sound a little bit more complex, it may sound a bit unnecessary. That is vastly, basically all cases, what you should be doing if you want to compare something against the length of it. You don't need the actual length, compare it against the length squared. The reason for that is that multiplications, multiplying x's and y's and maximum values, they're very easy to do, they're very quick to do. Taking the square root of something isn't easy. isn't quick to do. And when that method's called, you have an whole iterative algorithm has to go through to work out what is the square root for it. So that's an expensive operation to do. So it's much, much quicker to call the length squared and to square the distance and compare that than it is to work out a precise length. Other methods within this, we can set it, we can add other vectors, we can subtract, we can multiply. So it's just normal things for working out the size. We can also normalize the vector. So this one we did do that. To normalize the vector, we do actually need to know the length, so we have to call the square root operation. And as long as the length isn't 0, then we are dividing the x and y components by that length, and that turns it into a unit vector of length 1. Okay, so this was the Asteroid, which was a type of sprite. Didn't really do much. Sprite was a type of game object. And these game objects and sprites, they're making use of our vector class. So these things fit together. The last one I show you in the first part of this demo is the actual game screen itself. So here we have a game screen. We are giving it a width and a height. So these are not pixel values. These are game unit values. And the actual bitmap I'm using for drawing this is actually bigger than 1000 by 1000. But when I'm thinking about the world within which my objects are moving about, I'm in my head going to be thinking about 1000 by 1000 size area. And when I say an asteroid, for example, has a width of 50 by 50, then I know relative to this level how big that is. I've got a couple of viewports. The screen viewport's the whole screen, that's fair enough, but the layer viewport's going to be just a bit of the layer that I'm drawing that is visible at a point in time. I'm going to have one game object, so it's just a game object that contains a large background image. So that's my background. I've got my player spaceship, which we'll be looking at in part 2. I've got a number of asteroids, which I'm randomly creating and positioning. And I have a number of AI-controlled spaceships. 5 of them will try to seek out the player, and 5 of them are going to be turrets that will always be looking towards the player. When I'm creating the game, so this is my game screen, I make sure I call the Superclass. I create a new screen viewport, and the region of the screen that I'm drawing to starts at 0, 0, top left coordinate, all the way across the width, all the way down in terms of the height. So I'm drawing, my screen viewport is the whole screen. I'm just drawing the whole thing. My layer viewport, now I've got you can see here that there's an if, and then I'm creating 2 different types of layer viewport. The if says that if the width is greater than the height, so this is working out what orientation is the device running in. Is it in terms of portrait or landscape, or in terms of the actual pixel density on the screen? And it assumes basically square pixels. Based on that, we're going to create a viewport that reasonably maps onto the screen. So our viewport will take into account the orientation of the screen and will roughly match that in terms of its own particular size. So we are sort of scaling things. We're assuming sort of the 240 by 480 in terms of or 240 here, 240 that our viewport size, but scaling that by the portion, the particular ratio that the screen has. So that makes it look reasonable, not stretched, sort of occupy the whole thing. For loading in, we're loading in a whole bunch of assets here, and in this case it does make sense to put them into the asset manager, because we're going to have 20 odd asteroids that are making use of these 2 bitmaps. So we don't want them to load in their own copy, we want them to share and make use of it. And ditto with the other ones. Here we're creating our background. All we do for the background is a new object. Its center position is in level width divided by 2, level height divided by 2. So we're centering it in the middle of our world, and its width and its height is the width and height of the world. So actually our background object is sized to be the same size as our game world, occupies the whole game world. What image do we use for it? We go to our game, get the asset manager, and get out our space background. And it belongs to this particular game screen. Here we're creating our player spaceship. All it needs to know is where it's been created and what screen it belongs to. We've got a bit of randomness coming in here for asteroids. So we're creating a new list, array list in this case. We're going through it and we're adding in new asteroids at random positions within the particular level. And we're doing more or less exactly the same thing for our two types of AI controlled spaceship, the seekers and the turrets, randomly positioning them. A few methods here for getting out the spaceship, or getting out the list of AI spaceships, or getting out the asteroids. Now, the reason for this, what we'll see in the second part of the demo, but some of these objects, for example, the AI spaceship, if I have an AI spaceship that doesn't want to bump into, for example, the player, or bump into the asteroids, it has to have a way of getting access to, well, where's the player at, where's the asteroids at? And these will be the methods it will call, then will give it access to it. Update and draw. Now, you might think, well, there's quite a amount of stuff in this update method. It's basically all viewport stuff. What do we do? We update the player first of all. I'm then going to scroll down a little bit. We then update each of our AI controlled spaceships, and we update each of our asteroids. Now, the asteroids simply rotate, so when we update them, all we're doing is just changing their orientation. The rest of the stuff that we have here is all viewport. Well, sorry, that's all viewport related. This is player related. Because we are letting the player fly about the level, and we've set our game world as 1000 by 1000, we don't want to let the player leave the level. So we check to see, we get the bounding box for the player, and we check to see, is the player trying to go off the left-hand side, or trying to go off the right-hand side, or off the bottom or off the top? If that is the case, then we basically restrict the player location within the level, so they can't leave the level. You'd be right in saying, okay, why did we not do this in for the other one? And you could actually bound the AI-controlled spaceships to keep them in, but we're not doing it here. If they want, they can fly off, but their steering will bring them back. Once we've ensured that the player can't leave the level, that they'll bounce up against the walls, we then think, okay, we want our viewport to be focused on the player. So wherever the player is, that's what we will be looking at. So there we say, we know where the player's position is. We've updated the player. We've made sure the player's still within the world. So the X and the Y location will be valid. We then change our viewport, so the center of the viewport is looking directly at the player. And the final thing we have down here is that if the player is, for example, down in the, say, the bottom left-hand corner of the world, and if I were to center my viewport here, I don't want my viewport to try to see off part of the screen or under the bottom of the screen. So I do one final check at this point to make sure that my viewport can't leave the level. In other words, the bit of the world that I get to see has to be fully within the world. I can't try to draw a part of the world that's outside of my notional defined region. So there I check to see if the viewport tries to leave the world, then make sure the viewport remains within the world. For drawing it out, reasonably straightforward. We're simply clearing out the screen. I'm using a clip here, so we are the screen viewport, but we are going to clip any of the things that we draw to that particular viewport. The reason we do that is that if we're drawing using the matrix, we draw out the whole image. And if I had a screen viewport that was only drawing, say, a side-by-side view, only drawn to a part of the screen, then I don't want to draw outside of that actual defined part. So I can set up a clip region to make sure that if I do anything in here that tries to draw outside of it, it's just ignored. So I draw the background first of all, makes sense. Then I draw each of the asteroids, draw the AI controlled ships, and then draw the player finally on top of all of those. So that's all we want to have a look at in part one. In part two, we'll actually get down to the nitty-gritty of the of looking at the steering algorithms and how they actually work.